Garibaldi Park, in our backyard. Quite an astonishing geography and quite an astonishing geology. What I really want to do tonight is take you through Garibaldi, but with a real lens on the geology that stands behind a lot of the landscapes that you know and you're familiar with, and really sort of dig into those stories. And so what I wanted to do tonight, talk about sort of 6 big ideas that really then provide a frame for Garibaldi Park. And the first is the Earth's surface is really a mosaic or a patchwork quilt of different rock types side by side. From one rock type to another, you can go from very different geographies because rocks behave differently, they weather differently. Anyways, so here we are on Panorama Ridge, just downhill from the viewpoint. We're looking over to the Tusk, Black Tusk, and then beyond to the Ashley Range, Cloudburst Mountain and Ashley Range. In that one little piece of landscape, there are 3 completely different rock types, 3 completely different ages of Earth history. We're standing on a ridge made of tilted layers of ancient seafloor, about 100 million years old, that make up that entire ridge. Because they're a relatively soft rock, they create the soft landscape of Panorama Ridge, make it a great sort of easy cruising ridge. The Tusk itself, vastly younger. We go from a 100 million year old rock to 200,000 year old rock. And then in the far background, the granite peaks that are about 150 million years old. So, and they represent not seafloor, not sort of a volcanic product produced on the Earth's surface, but something that probably formed 20 kilometers deep in the Earth, and now is at the Earth's surface and forms the rugged granite peaks of that terrain. The second big thought is that we had an ice age. And in geological parlance, it was literally yesterday. It just ended. It just ended 10,000 years ago. And that means that the landscape we see today, it's really hard to see much that isn't molded by the ice age. What isn't is what's formed since. Things like the Fraser Delta and river valleys that have sort of filled in with river sediment since. But by and large, most of the landscape that we see is a product of the ice age. And this is sort of an interesting photograph taken at the edge of Greenland, and it gives us a bit of a clue into what the ice age meant to this landscape. If you look in the far distance, you're looking at the ice cap. I mean, nothing pokes through it. It essentially mantles the entire landscape. As you approach the coast, the mountains start to poke out. And as you get right to the coast, only the lower parts of the valleys, in fact, have glaciers running through them. And in a sense, that's a bit of a sort of a time travel from the interior of Greenland to the coast is a bit like transiting from 15 or 16,000 years ago when most of British Columbia looked like the interior of Greenland, and the coast where the ice had largely melted back and it was only big glaciers in the valley bottoms. You can see that almost any landscape, if you get a bit of a view where you can see the high peaks and you can see the valleys, you'll notice an interesting feature, and that is the lowest landscapes are the smoothest landscapes. And the intermediate ones are a little more craggy, and it's the highest peaks that are the only thing that really look rough, irregular, and craggy. And that reflects the fact that ice has essentially scraped and molded the landscapes at low elevation. And the lower they are, the thicker the ice was over them, and the more the grinding impact of the ice. And so that's just a feature that you tend to see anywhere. This is a view from Horseshoe Bay with a telephoto lens looking at Boyer Island and then off to the High Tantalus Range. Now the Ice Age ended 10,000 years ago. But since, and at that time, that was the end of anything we call sort of like a continental scale glaciation. But through that last 10,000 years, essentially the alpine glaciers persisted. And through time, they advanced and retreated and advanced and retreated. And really interestingly, the last big advance peaked only 200 years ago. And what we're seeing today is the retreat of a very significant advance. From about 1300 AD to about 1850 is referred to as the Little Ice Age. And we see on the landscape features like, we're looking here at the Warren Glacier. Garibaldi's just off the side here. This is the table. That's Castle Towers here. We're looking east into the sort of the granite country of eastern Garibaldi Park. So this is the headwaters of Culleton Creek right here, heading down here. That's the Orange Bridge that you cross on the Highway 99. And you can see this big debris field that extends over here and has pretty sharp boundaries with the forests here. And this is pretty rough artwork, but essentially that's what the Warren Glacier was in 1800. It's an astonishing retreat of ice. The ice mass lost in the Coast Range over the last 100 years is astounding, and it's left a legacy of these great gravel barriers. Okay, big thought number 4. We're in a collision zone. And this is, I'm sure you've heard this story many times. This is the reason why we worry about the big shake, the big mega earthquake. Last occurred in the year 1700, and we're pretty much due for the next one sometime. Anyways, the reason for that is that coastal British Columbia sits at the juncture of 2 giant Earth tectonic plates. And the North American plate is steaming westwards. Atlantic Ocean is opening, and the result of that is North America is moving westwards, and it's essentially driving over top of an ocean plate which happens to be denser, and therefore it sinks. And this thing is called by geologists a subduction zone. It's a collision zone, but this particular form is referred to, you might have heard, as a subduction zone. And so the earthquakes, and the biggest earthquakes, are along this boundary zone as it sort of sticks and slips and sticks and slips. So that's sort of a big picture. Well, that's important to us because the inevitable consequence of a subduction zone is volcanoes. And if there's one thing that Garibaldi is about, it's about volcanoes. And so, in a sense, and of course this is just a very artistic rendering, this is, in a sense, the plumbing system of Garibaldi volcano and the other Cascade volcanoes like it. What happens is that the ocean crust up here essentially interacts with seawater, and essentially water gets incorporated in the mineral structure of this ocean crust, and then it slowly, moves down to deeper, higher temperatures and pressures. And what that does is it causes the water to be released as the minerals transform. And in doing that, essentially it becomes a catalyst for the melting of rock. That melt, liquids are less dense than solids, so it tends to rise. In mysterious ways, that melted rock moves its way up, and eventually, if it makes it to the surface, it's essentially a volcanic eruption. So when you see Garibaldi, remember that this is sort of almost like a fungus on a tree, where what you see, the fruiting body, is just a tiny piece of a vast network. Like Garibaldi is the same. It happens to be dormant at this point in time, but it does have this whole 20 kilometer, 30 kilometer, 40 kilometer, 50 kilometers network of plumbing that essentially is the feeder system to the volcanic eruptions. So Garibaldi is just one of a family of volcanoes that extend from northern Vancouver Island down to California. It's the Cascade volcanic chain. Their logic is the same as Garibaldi's. They form a line because they're just at the right distance inland from where the subduction goes down, such that the subduction zone is all at the right depth to release the water that causes the melting that makes the liquid magma rise. So now what's interesting about this figure, there's the line of volcanoes. This happens to be sort of a little chart that just shows when each of the volcanoes have erupted over the last 4,000 years. And the best thing about this little chart is that while the American volcanoes are just going like stink and blasting or erupting pretty frequently, once you get north of the 49th parallel, things get pretty quiet. And I think that's my favorite volcano is the dormant volcano. And that's what we've got. And you can see that Garibaldi has been completely quiet over the last 4,000 years. In fact, the youngest eruption in the Garibaldi belt is about 9,000 years. So it's interesting to see Mount St. Helens here, the last to erupt, was also the most frequent to erupt over the last 4,000 years. And geologists, when asked before 1980, when it last erupted, what was the most likely cascade volcano to erupt, just looking at the eruption history, they pointed to Mount St. Helens. Fifth thought is that the entire eruption history of the Garibaldi area, and there are, I'm not sure, maybe 10 or 12 volcanic centers in Garibaldi Park, each of them separate little volcanoes, only one big one. All of them happened during the Ice Age. Now the Ice Age sort of came and went, came and went, came and went. It was a series of ice advances and then periods when there was ice was very confined. But nonetheless, Garibaldi is famous to geologists because of this story of fire and ice. Volcanoes, when they interact with ice caps and ice sheets, just do funny things. They create shapes that are unusual. And we'll take a look at that. And they're analogous to what's going on pretty much literally as we speak in Iceland today, where you have a volcano, that whole island is just one essentially big volcanic pile, where those are erupting through the ice sheet and you get remarkable events.